So I will get back with the previous formulation we were using. I will start, or maybe resume with this step. We stopped here. We have like a sum from I equals to 1 to m, which are basically our classifiers. So we have a bunch of classifiers here, and we are measuring the empirical risk from one classifier fi to its expected risk, like this. And if that is greater than or equal to some epsilon, there are some different formulations. If you get like there are books which doesn't use the equal sign but just the greater than. But actually it's an open ball, and that open ball might have, topological terms, it's like an open ball. So you can have an open ball with a boundary or without a boundary, and that doesn't make like a great difference. But anyway, and we stopped here, summing up on the other side also the terms from 1 to m, which are equal to 2 times the exponential value of minus 2n. This is epsilon. Let me make it better. Epsilon squared. This is after the law of large numbers. But actually, I just did not provide something that's very, very useful and very common to be used. There is like a short notation for that, and I believe that's probably interesting to introduce now. That notation is like this. We can say that Vopnik was interested in formulating the statistical learning theory like this. The probability of the supremum value for every function f inside some bias, inside some learning bias, in terms of the empirical risk of that function and the expected risk of the same function to be greater than or equal to epsilon. That's somehow, actually, we can exactly compute this guy. If we have a set of functions, I'm gonna say something about that afterwards, but before maybe we could remember those terms just to bring back the notion of the risks. So here I have some risk or error in a sample, or error in a given sample. It's always in a sample. And here we have the expected risk, which is in the whole population. What means that I have to have access to the joint probability distribution to compute that. So it doesn't matter if I have like lots of examples. Could be like 1 million, 1 billion examples. As far as I don't have access to the joint probability distribution, I just can't compute this guy. It's just uncomputable, in fact. So there is a way of dealing with that guy. We're going to talk about that later. But before, I think you guys remember last time we were discussing that this could be computed somehow using this probability. So this is actually the same as the probability of a function, the empirical risk of a function being selected. Let's say the first function, the first classifier inside some bias, minus the expected risk of the same classifier to be greater than or equal to epsilon, or the second, the third, until the last classifier we have inside that bias. So somehow we are supposing there are countable classifiers inside the space, inside the bias of some learning algorithm. This is actually the same. So it's like instead of using just one of those functions, I'm using the worst case scenario. I'm just deciding to select the worst possible function inside this bias. What this means, it's better draw that, because that's going to be easier to understand, I suppose. So if I have a space, like could be a square like this, representing all possible functions in the universe, every function, And it's not difficult to imagine that. Could be the functions we know and functions we don't know. But just to remember, if we consider a Gaussian mixture, which is a universal approximator model, we could build up f all with a combination of several, of infinite Gaussian functions, because that's going to it's going to approach the universe with all those functions, just because there is a proof that that provides an universal approximation for any kind of function. So on top of that, somehow I select a bias. That bias is this uppercase F, this guy here, is that guy. Okay, so somehow inside this bias I have the possible classifiers. Let's say here I have one of those classifiers. Let's say this is Fk, for example. And that Fk could be like a hyperplane dividing the space. So on one side I have some positive examples, and I have negative on the other, and one is being missed somehow. So I lost. I don't have like the best as possible result for that, but that's a possible classifier. Somehow it's a possible classifier. So here we have all of them, and actually when we decide to represent in terms of the supremum value, we are comparing functions. That's the same as having, exactly, yes, actually, as having on one axis we have all those functions, all possible functions, all functions in F, in uppercase F. So just imagine that we somehow have like an empirical risk in terms of all those functions. And the expected risk, let's suppose it is this. So in terms of the supremum, we are measuring the worst case scenario. So we are measuring this quantity, which is the greatest difference in between the empirical and the expected risk. And why is that important? Basically because if in the worst case scenario, I somehow measuring that worst case difference in terms of what we measured on a sample and what we are going to measure in the whole population of unseen examples, if that somehow is very small, I can learn. What I mean is like if I build up a model from some data and I have an empirical risk like equals to 0.1, 0.1, or 0.01. And somehow when I apply on the real world scenario, let's say I have like 0.02. So this difference is something that I'm trying to reduce when I learn. Because as close those risks are, basically we have the same behavior, we expect the same behavior in the real world conditions. That's the same as saying if I had the chance to assess a bunch of classifiers and looking to those risks, those empirical and expected risks, I could say, okay, the best classifier we have here is the one that minimizes that difference of risks, just because, just remember, if somehow I have the same behavior on a sample and on the real world scenario, that's how it should be. That's actually learning. Of course, in addition to that, somehow I have also to reduce the empirical risk. So it doesn't matter if I have like both risks very close, could be like 0.5 and 0.5. That means they are very close because the generalization is happening, it's equal to 0, but that's a problem. We have to have that approximation between both, but we also have to reduce the empirical risk. So it's not just one condition, we have to satisfy both. That's a main scenario we have with the statistical learning theory. So every time we talk about the supremum, we're talking about this difference between two functions. And now I think this is easier to see because we don't have like a countable number of functions inside. I mean, let's say we don't have a countable, it's better to say it like that. Let's say we don't have like a countable number of functions inside the bias of some algorithm. So we have infinite functions. It's going to be easier to explain now. And so I have some sort of function in terms of those classifiers or regression functions we have inside the bias. And those are the empirical risk function and the expected risk. So the supremum is basically this difference. So somehow I want that difference to be not that big. If that happens, if I don't have such a big difference, I can learn. That's what's behind learning. Statistical learning theory, and not just statistical learning theory, but learning as a whole. So from that, I think it's...
Excuse me?
I just don't know what just doesn't work. Okay, yeah, of course, please.
Just recall me what is f compared to the set of all functions?
This f, you mean?
No, the capital F.
The capital F? The capital F is a bias. It defines to me the subspace of functions. The subspace of
Yes.
Is it good that
It's not for this.
Pen or it's not for this. And she gave some. Okay. Okay, no problem. So somehow you're shooting, but that's gonna be okay afterwards. So this space is the same as saying, for example, if I decided to use the perceptron, the perceptron always build up linear functions, right? So in terms of the perceptron, this bias contains just linear functions. If I decide to use the naive Bayes, for example, let's say I use a naive Bayes with a single hyperplane. Every time I decide to use the naive Bayes, the hyperplane is going to shatter, it's going to divide the space in an orthogonal way in terms of the input variables. Because every time, it's like a tree, the tree is the same. When I say, okay, if a value is greater than or equal to something, or smaller than, it's going to be different. So somehow I'm dividing that axis with a hyperplane. So it's easy to see now that in terms of a single hyperplane, let's consider we have just one, a naive Bayes with a single hyperplane has a bias which is more restricted than the perceptron with a single hyperplane, just because the perceptron can change the derivative of that hyperplane and shatter in more ways. So if I go from that to the multi-layer perceptron and I consider like lots of hyperplanes, that space of functions is even greater because it's going to contain inside several linear hyperplanes, and the combination of linear hyperplanes brings to us this non-linearity, this non-linear behavior, this non-linear capability of shattering the space. Okay, so somehow I'm gonna do something else. Okay, no problem. And then, for example, if I consider instead of a naive Bayes, for example, with a single hyperplane whose bias is very restricted, I consider a tree with several hyperplanes. All of them are orthogonal, always orthogonal, and I can show you why, but that's going to be more relaxed. So it's going to contain more functions, of course. So this space is basically the space we decide to use to take advantage to solve some problem. So when I say, okay, I'm going to solve a given problem using multi-layer perceptron or could be a decision tree, and just after deciding which is going to be the technique, which is going to be the algorithm to be applied, I am somehow defining the bias. I am somehow making it more restricted or less restricted depending on the algorithm, and also depending on the parameterization, because it's not just about the algorithm, because I could use, for example, the same algorithm having a very restricted bias, like containing just a single function, or maybe on the other hand I could have like a very a different situation in which I would have like lots of functions and the bias would be less restricted. So both are possible. Let me see if we have like, okay, we have like this is probably going to work. Consider we have like some points in a given space, and I have two attributes, and I'm using a decision tree here. So somehow every time I use a decision tree, if this attribute is like attribute A and this is B, and I say, okay, if A is greater than or equal to something, it's going to be the positive class, otherwise the negative. So somehow I am cutting like that with my hyperplane. So I am building up a hyperplane on top of that space, which is always orthogonal to that axis, that particular axis, right? Mm-hmm. So if I decide to use, for example, two hyperplanes here, like one here and another here, those, in the case of decision trees, they will be orthogonal to that particular axis, to this axis in this case. In terms of the multilayer perceptron, that doesn't happen. We have something different. We have a hyperplane with a derivative in terms of all possible variables, right? So it could be like something like this, or something like this, or something like this. It doesn't matter. It's going to change. So that makes an algorithm like multilayer perceptron, or maybe like let's extend. It's going to close eventually. Mm-hmm. For example, in the deep learning scenario, that's the same as using an architecture with more or less units, more or less neurons per layer. So if I have less neurons, I will have a space with less functions. If I have more neurons, I will have a space with more functions. And that's going to affect directly in terms of, in this guy here, and it's going to affect actually a lot in the supremum value and in the learning guarantees, of course. So this probability of the supremum value for all functions, that's the same as saying that for all functions inside some algorithm bias, this is the same as empirical risk and the expected risks, the difference in absolute value, just because it doesn't matter if it's negative or positive, it's just a difference, it's just a distance, that's why. Greater than or equal to some epsilon, that's going to be less than or equal to...
It's recording.
Sorry?
It's recording.
No, it's not there, but no problem, because we changed that. This is going to be equal, as I said, to the probability of selecting either F1, either F1 or a second classifier inside the same bias, F2, or until the last. Let's say we have a countable number of classifiers or regression functions inside that bias, just because that makes things easier to understand now. And that's going to be the case afterwards, not now. Okay, so this is equal, and I think you guys remember last time I was discussing that the law of large numbers is valid since I select a function like f1 out of the bias, out of the whole space of functions f I have here. So if somehow I select f1, just without considering data, I mean, the law of large numbers is valid. If that f is selected by our classification algorithm, somehow biased by data, the law of large numbers is not valid. So in that situation, as I am using all possible classifiers inside that bias, the law of large numbers holds. So the law of large numbers holds here. So as it holds, I have that for every probability like this, it's going to hold. But before that, somehow I need to simplify this probability. And what I did last time with you was this. This is the same as a space where I have, for example, areas, and some of them have intersections. So let's say I have an area A, B, and C here, and here they have some sort of intersection. So in terms of probability, if I have either this or this or this happening, and here also either A, B, or C happening, the total probability is going to be always upper bounded by the sum of all those probabilities, by the sum of A of the probability of A plus the probability of B plus the probability of C. And in that situation, of course, I'm getting an upper bound. I'm just considering twice all those intersecting areas. So it's an upper bound, maybe far from the ideal, but it's still an upper bound. That's what Vapnik did. So Vapnik did this. Okay, so this is upper bounded by the sum of every function, the probability of every function. So from that, from Fi, okay, and here we have the expected risk to be greater than or equal to some epsilon. From that, we have a term that allows us now to use the law of large numbers, because the law of large numbers is just in terms of the probabilities of single functions. So if I have the probability of some empirical risk given a specific function and expected risk given that specific function to be greater than or equal to some epsilon, this is going to hold. It's going to be 2 times the exponential, the negative exponential value of minus 2 n epsilon squared. So this holds for single functions. So in this case, as we are summing up those probabilities on both sides now, okay, now we have 2 sums. One sum that goes from 1 to m here, and that's going to be I here, just changing. And this is going to be the same, like from 1 to m. So on this side, I will have this sum, which is here. And on the other side, we have an upper limit. And that's the most important part now. I will have this upper limit. And that upper limit is going to bound this probability. And of course, bound the supremum. And that's the most important part. So somehow, I'm just going to rewrite now, because it's going to be easier to see. That's the same as 2 times m, because I have a sum of 2 times the exponential value of something that's negative. So as we have like a sum of m terms, that will be 2 times m times the exponential of minus 2n epsilon squared. So this is the most common formulation. So we have the supremum for f in f. This is the most usual way people see in books and papers and whatever. Greater than or equal to epsilon. This is going to be smaller than, upper limited by 2 times m, the exponential of minus 2n epsilon squared. In fact, now we have the typical way of showing the statistical learning theory. That's a typical formulation people use. And as I discussed in the previous week, actually a week for you, and the video, like, I don't know, it doesn't matter. This is going to be a function, and that function is called the shattering coefficient. And the shattering coefficient, in my opinion, is the most important contribution or the most important thing we have in machine learning. In my opinion, this is the most important function to pay attention, because that's going to somehow define my bias. It's going to tell me how big my bias is, and that's what we're going to discuss today, basically. So I will have a space with all the universe of all functions, and inside, if I have, for example, the perceptron, I will have a bias like that. If I have a multi-layer perceptron with 2 neurons, for example, in the hidden layer, it's going to be more relaxed. A multi-layer perceptron with 2 neurons. If instead of that we have a multi-layer perceptron with 5 neurons, for example, it's going to be even more relaxed. And that's something we can compute now. We can at least estimate and verify how that works. As I told before, if I have just a single hyperplane, just remember, and if I have a 2D space, input space, where I have like a variable like x1 and x2, and I have a single point on that space, I can classify that as positive and negative. So I have two possibilities. For a single point, I have two possibilities. Those are the number of distinct classifications. The distinct classifications provide the shattering coefficient to me. Okay, so here I have the sample size. So for 2, as we saw before, we have 4, right? For 3, in this case, we're going to have 8. But for 4, somehow we don't have 16, we have 14. And from now on, if I grow the sample size, if the sample size increases, it's not going to behave like an exponential function. It will behave as a polynomial function, while here it has this exponential behavior. And the most important here is this point here, the last sample size where we have the exponential behavior is known as the Vapnik-Chervonex dimension, which in this case will be equals to 3. So in that scenario, now I think we better estimate some shattering coefficients. I will start by estimating the shattering coefficient for the perceptron, and then we could compute for the multi-layer perceptron, for a multi-layer perceptron with more neurons, so we can somehow understand how is that going to influence this equation.